So today we are going to complete discussion on Pwm techniques. We still have one small section to cover, and after that we'll be discussing on soft switching techniques, which is in chapter 8. The only topic we haven't covered for Pwm techniques is Pwm rectifiers. Actually, this idea is very simple if we have the correct viewpoint on this thing. Now, based on the previous discussion about Pwm techniques, we have already had this understanding that a Pwm controlled inverter, let's see, as we showed here in the picture in the screen. Okay. This is a single phase. Let's see, we are looking at the single phase bridge. Pay attention to the way I'm drawing this diagram. Usually, if I want to draw this diagram, I want to draw these IGBTs and diodes first. And then I connect all these lines. Okay. Let's say this is a single phase bridge inverter, and the right hand side this is DC side, that's DC, and left hand side this is AC. Usually we do it in the reverse way. We put the input on the left hand side, output on the right hand side. Well, that's okay. You have to be adjusted to all different ways of drawing this circuit diagram. Okay, this is a voltage source, single phase bridge voltage source inverter, and therefore, with Pwm technique, I can always realize this AC voltage here. This is the AC side. Let's say this is point A and B. This voltage between A and B, UAB, I can always make sure with Pwm technique, this voltage is very close to sine wave with certain frequency and magnitude. Okay. And usually this inverter is connected to the load, and usually the load is, let's say, if I have a inductor and resistor, this is the inductive load. Okay. Okay, this is the usual case, an inverter connected to a AC load. And therefore, if we understand this UAB can be very close to sine wave, then we can always consider that with this voltage source inverter under Pwm control, we are actually generating between point A and B. Let's see, this is A, B, between point A and B, we are generating a AC voltage source with voltage UAB. and this UAB is a sine wave. Okay, this is equivalent to that. You can always consider this circuit as this equivalent circuit diagram. We are generating a voltage source, sine wave voltage source, connecting to the AC load. And therefore, this is a sine wave AC source. This is the AC load. Therefore, I can use what? I can use phasor to represent this circuit, represent the variables in this circuit. Okay. For example, I'm using this UAB dot to represent the phasor of this sine AC voltage. Okay. And use phasor method, we can analyze the circuit. We can analyze how much current, this current it is. Let's say this is the current I. And then I can obtain through this phasor, if this is known, this inductance is known, this resistor is known, then I can calculate the magnitude and the phase angle of this current. That's the phasor method. I can make sure that this current is also sine wave, because this is sine wave, this current should also be sine wave. Now, this is the case when this AC side is only inductor or resistor. We call that passive load, because there is no source in the load. This is one case. But very often, this voltage source inverter can also be connected to this kind of AC side. In the AC side, you not only have inductance, reactance, but most important, you have AC source. That is AC grid. That's the grid voltage. Okay, therefore, we can redraw this circuit diagram in this way. Very often, this voltage source inverter can also be connected to something like this. And this is the grid voltage. Okay, and this is resistor and inductor can be considered as the inner impedance of the grid. Okay. Okay, that's the very often case. So let's see how this circuit is working. Okay, a voltage source inverter connected to the grid. How this is working? If we understand this, let's see when this voltage source inverter connected to an AC load. For this case, we can use a phasor approach, phasor method, to do an analysis on the circuit. Then very naturally, we can also do that analysis for this case. Because if we control this voltage source inverter still under Pwm technique, then the voltage between point A and B can still be considered as a controlled sine voltage source. Okay, therefore, the equivalent circuit for this circuit would be, on the left-hand side, you have this AC source voltage. This is a grid voltage. I'm representing that with a phasor. Okay. And then you have the inner impedance of the grid. Okay. This is the US. That's the source voltage. AC a grid voltage. And then you have the impedance of the inner impedance of the grid. And then between point A and B, for this this voltage source inverter under Pwm control, we can always consider that as a sine voltage source. Therefore, I can use another phasor still to represent the voltage you generate in the AC side of this voltage source inverter, UAB. Okay? So this will be the equivalent circuit. And therefore, you have any question? Well, I'll be talking about that soon. Okay? In this case, the AC side voltage, because that's grid voltage, we cannot change that. So for a phasor, the phasor representing the grid voltage, it does have a fixed magnitude and fixed frequency. Fixed magnitude and fixed angle. The magnitude and phase angle for the grid voltage is fixed. We cannot change that. That's coming from the grid. But what we can do is we can change this. We can change the magnitude and phase angle of the AC sine wave voltage generated by the voltage source inverter. Okay? We can do that. We can control this. We can control the magnitude and phase angle of UAB. And therefore, we can imagine in this equivalent circuit, this is very simple. You have an AC source in the left-hand side, another controlled AC source on the right-hand side. So by controlling the magnitude and phase angle of the voltage source inverter, we can control this current, IS. This current IS, we can control the magnitude and phase angle of IS. And on the right-hand side of the screen, you can see there are different cases when we control the magnitude and phase angle of this current under different mode. Let's see, in case A, you can see this IS can be controlled so that it has the same phase angle as US. Same phase angle. That means this current IS is having the same phase angle. It is sine wave and has the same phase angle of US. That means this energy, power, is generated from here and transferred to the right-hand side. Okay? In case B, we can control this magnitude and phase angle of IS so that the phase angle of IS is exactly reverse. Okay? The phase of the IS is exactly reverse to the US. Okay? So that means if, let's say, US is something like this, then IS is reverse, exactly reverse phase angle. This is IS. Okay. That means what? That means if you look at the power generated by US and IS will be exactly negative power. That means what? That means that power is actually transferred from right-hand side to the left-hand side. Okay? So in both of these cases, you can see in case A, power is transferring from grid to the right-hand side to this inverter and to the DC side. So power is transferring from AC to DC. That is rectifier. Right? Changing from AC to DC, that is a rectifier. Therefore, under this mode, we call that Pwm rectifier. This voltage source inverter is actually working under the Pwm rectifier mode. Okay. On case B, you can see the energy is transferred from DC side to AC side because this power generated by the grid voltage source is negative. So energy is transferring from right-hand side to left-hand side. From DC to AC. And therefore, this is the inversion mode. Okay. So that's this voltage source inverter is exactly working as a inverter, transferring DC energy to AC. Okay. So very naturally, you can also think about other cases. We may not control this current exactly in phase with the grid voltage or exactly in the reverse phase as the source grid voltage. We can control this current with any phase angle. Okay? Particularly in phase C and D. Okay? Particularly in these two cases, when this current is having the phase angle leading the grid voltage by 90 degrees or lagging. I can also, another case, I can also control this lagging to the US by 90 degrees. That means what? That means what? So if I draw the time domain waveform, if this is the voltage US, when the current is leading US by 90 degrees, that means what? The current is here. Okay. Current is something like this. This is the current. Okay. And therefore, if you calculate the active power, that active power is 0. Okay. It has only reactive power. So in this case, we are absorbing reactive power from the grid and absorbing no active power, only absorbing reactive power. Okay? You can also control this current to the phase angle so that I is delayed to US or lagging to US by 90 degrees. So therefore, the current will be like this. Okay. Again, this is phase angle is different to US by 90 degrees. Therefore, there's no active power. There's only reactive power. But this reactive power is we are absorbing lagging reactive power. In the previous case, we are absorbing leading reactive power. Okay, one is this leading reactive power is capacitive. This is called capacitive reactive power. This lagging reactive power is called inductive reactive power. Okay. So anyway, we can control this current. We can control the magnitude and the phase angle of the current we are absorbing from the grid at any phase angle and magnitude as you want by controlling the AC voltage of this VSI, by controlling its phase angle and magnitude. So this is very interesting. Okay. Through a voltage source inverter, we can actually control the direction of power transfer, and also we can control the amount of active power and reactive power we absorb from the source. So this is a very good device. This will be a very good device for the electric grid. I will talk about this application in the future. Okay? So in this sense, this voltage source, this circuit diagram, voltage source inverter, usually we do not call that voltage source inverter. We call that voltage source converter. Because this could not be working, could be working not only under inverter mode, but also under rectifier mode or under reactive power, pure reactive power generation mode. Okay? So we call that voltage source converter. C means converter. Converter means we do not identify whether this is inverter or rectifier or reactive power generator. It could be anyway. So voltage source converter, VSC. Okay, that's the basic idea. If you understand this, then I will not get into details of the following part. This is the example of single phase. You can do this for three phase. Okay, the basic idea, operation principle, exactly the same. A question?
In case C, it means that C or grid changes to a reactive system, yes? Because active power is 0.
Pardon me? Would you say it again?
In case C, reactive power compensation.
Yes.
Active power is 0.
Right?
But we know that in a real system, generator cannot produce only reactive power. So it's a paradox.
Okay. You are right. For case C, that's the ideal case. When we keep this current exactly at 90 degrees leading or lagging to US. Therefore, there's exactly no active power transferring between the grid and the load. Okay? But in the ideal case, there's always energy loss. For example, here, you have a reducer here. And there will be energy loss on the power semiconductor devices. This will have some energy loss. Therefore, that means you do need to transfer some energy to the right-hand side. And therefore, that means what? That means this angle, the phase angle of the current, can be controlled not exactly 90 degree leading, but with certain angle difference, not exactly 90 degrees. And therefore, we are absorbing not just reactive power, but also a little bit of active power. Okay? But that's the real, in the practical case. You are right. Okay? In the following part of the lecture notes, there is a discussion about the three-phase case. I will not get into details in the class. You read through the lecture notes and the textbook after the class.